we just complete the topics existence and uniqueness of solutions for first order ODE. Yeah. Now we move to second order ODE. Yeah. The second order ODE, from the title you can see, we work on homogeneous second order linear ODE and parenthesis initial value problem. Yeah. Yeah. So actually there are two parts. Yeah. The first part, yeah. So there is a existence uniqueness result for this IVP problem. But the IVP is a homogeneous second order linear ODE IVP problem. Okay, initial value problem. The second part is not IVP. Okay, so homogeneous. Yeah. So here, that's why you see, put it in the parentheses, because the second part we just work on the homogeneous. Okay, not IVP. Then we consider there is another result about its solution, about the general solution result. So two results here. All right, the first one, the homogeneous second order linear ODE, the standard form like this. Then we add a initial value condition. Two initial values we need. Yeah. All right. Then let's look at the result of the theorem, existence and uniqueness theorem. Yeah. First, look at the condition. Under what condition we have this result? Yeah. The condition, we look at the P function and the Q function. These two functions should be continuous. So here you can see the condition is pretty weak, only continuous. We do not require these two functions differentiable. Yeah. So we know differentiable condition is stronger than continuous condition. So not necessarily differentiable. Yeah. We only require continuous. Okay. All right. On some open interval I containing x0 value. Yeah. The initial condition is on this x0 point. Yeah. But we need a neighborhood. So here the open interval I is used as the neighborhood containing that x0 point. Yeah. All right, so that's the condition description. Conclusion, then the above initial value problem has a unique solution, y of x on I. So here you can see has, that's the existence, right? Yeah. Has addresses that existence issue. That unique solution. So here you can see this theorem covers both existence and uniqueness. Yeah. So very simple. Yeah. Here you can see, comparing with our first order result. Yeah. So you can see even simpler. Yeah. Yeah. We only require these two functions continuous. Yeah. Yeah. But if you look at the first order, the f function, we also require that continuous. Yeah. But there is a bounded, right? Yeah. So there is a bounded condition. Yeah. But here you can see we only have that continuous condition. Yeah. All right. This is the first result. The second result. Then we do not use the initial condition. Okay? Yeah. So we only look at the homogeneous second order linear ODE without initial condition. And we want to represent its general solution. So this result is about its general solution. So the same PQ continuous, because here there is no x0. So we do not need to mention that x0, because it's not an IVP problem. All right. Then the conclusion is this homogeneous equation has a general solution on y of general solution on I, open interval I, and its general solution should take a specific form, a linear combination of two solutions, and every solution capital Y of X on I. First, this tells existence, right, has a general solution. So this is the existence part. All right. Then we want, definitely it's not unique, because general solution, there are infinitely many general solutions. So for this one, we do not look at the uniqueness, because it does not make sense. This one, we know general solution, we always have infinite many solutions. And every solution capital Y. So here you can see this place we use little y, this place we use capital Y. Because the emphasis is different. All right. Because here we want to cover all the solutions for this homogeneous equation. Remember, let's imagine all the solutions of the homogeneous we represent. We use this big circle represent. Okay, all the solutions of this homogeneous second order linear ODE. Now, every solution. So you pick any one of the solution in that circle. Anyone you pick in that circle. So we use that capital Y of X represented. For it can be represented as a linear combination. Capital C1, C1, C2. So it's not important to use capital C or little c. That is not important. All right. I think here the author uses, because here is capital Y, so then also use the capital, but that is not important. Where little y1, little y2 is any basis of the solution. That's the second result. So any solution in that big circle, you can represent it as a linear combination of two basis functions, basis solutions of this homogeneous linear system, second order ODE. All right. And some of you may feel, this result looks not special, right? This result looks, nothing new, right? Here I try to guess your possible feeling. So how do you feel about this? Because based on what we have learned so far, it looks like we should have this result, right? Yeah, but actually, this result has some special points. Not that trivial. Yeah, here I want to say, some of you may feel this result looks pretty trivial, right? Yeah, because that should be the way it is. Yeah, this kind of feeling. Okay, so here I want to, make some comments about this result. Actually, this result is not that trivial. There are some special points. Yeah, not that natural. Okay, although this theorem should be proved. Yeah, but here we do not prove theorems. Yeah, we only work on formulas. Yeah, we do not do the proofs. Yeah. So here there is two special points that make this theorem non-trivial. Non-trivial. Yeah. The first point is any solution pick from this big circle. Any solution, anyone. So you can represent it in this form. Yeah. That's non-trivial. Yeah. Yeah. That means you can choose two basis solutions that you can represent all the other solutions using linear combination. Yeah. That's non-trivial, right? Yeah. Because you need to make some effort to prove it. Yeah. So that's the first point, non-trivial. Yeah. The second point, also non-trivial. Yeah. That's the another statement. Yeah, here. So that is, there is no singular solution. Singular solution. Yeah. I mentioned this concept before, but I feel most of you probably already forget this concept. Yeah, let me repeat this. What's the meaning of a singular solution? Yeah. All right. So, yeah, because I remember in this homework assignment, I give you a concept question about singular solution. Yeah. So you should know about this concept. Yeah. All right. You know general solution and a particular solution, that relationship, right? Yeah. So this concept related to the relationship between the general solution, usually we have large, infinite many general solutions. Then a particular solution. Okay? One particular solution. You just select, C1, C2 with concrete values. Yeah. C1 equals certain constant value, C2 equals certain constant value. That is a particular solution. Okay? All right. So here you can see, to get a particular solution, you just choose certain constants then from the general solution. So then you can get a particular solution. Yeah, that's the relationship. But then there is a special case. That is, you may have a solution. Yeah, you may. Yeah, so there is a situation. Okay. You may. That means sometimes you have, sometimes you do not have. Okay. You may have a solution not from the general solution. Okay? Yeah. So what's that? That means no matter how you choose C1, C2, no matter how you choose C1, C2, you cannot get a solution, one special solution here, okay? Yeah. Sometimes, and if you have this kind of special solution, then we call it is a singular solution, okay? It is a singular solution. Yeah. And we saw it. Yeah. Yeah. Probably you already forget about that. So we have an example. Here there is here we use the first order ODE. Okay. Yeah. So we have an example from first order ODE. That is logistic equation. Do you remember? Logistic equation. Okay? So what's that logistic equation? Y prime equals capital A constant times 1 minus capital B y squared. This is the logistic equation. Alright? Yeah. And we can find a solution easily. Okay? Yeah. So its solution, it's a general solution, equals capital A over constant little c times e to the negative a over b t plus b, okay, something like that, okay, yeah, something like that, yeah. Look at this expression, okay. This is a general solution. Yeah. A is fixed, B is fixed. Yeah. C you can change. When you change little c value, so you get a large number of infinite many of particular solutions. Yeah. So this so that's for the logistic equation. But this equation has a special solution, y equals 0. You can see if you plug in y equals 0, it is a solution, right? But you can see this y equals 0 you cannot get a y equals 0 solution from this general solution. Because this general solution, capital A is non-zero, okay? The numerator is non-zero. Then denominator, whatever it is, the denominator, the whole number cannot be 0, okay? Yeah. That tells us this is a particular solution. Okay? Yeah, that's from the logistic equation. We have that special example. Yeah. All right, but this result tells us here is for the second order ODE, homogeneous linear second order ODE, there is no singular solution. Okay? Yeah. So that's this statement in the parentheses. There is no singular solution. Yeah? So that's non-trivial, right? Yeah, that's non-trivial. Okay? All right. Yeah. All right. So here I just remind you the meaning of the singular solution. Yeah. All right. Yeah. So here you can see we although the main work for this course, we need to do calculation to solve real-world application problems, but you need to have some theoretical background, because this theorem is important. Theoretical result, these theoretical results important. So I spend a lot of time to explain, these results. Yeah. Then, after that, I may give you concept questions about, so you will see, you will have many concept questions about these results, existence and uniqueness theorem. Okay? In your quizzes, and in your homework assignment number 2. Okay, yeah. So then you will see several such questions. Existence, uniqueness. Yeah. So you need to understand these results very well. Yeah. All right, so that's the first topic. The second topic, B.5, Wronskian for linear independence. Yeah, remember we talked about one question: how to check linear independence, right? Yeah. So not just for two functions. So we want to check a linear independence for y1, y2, yn. Yeah. So we have n functions. So we need a convenient way to help us check if these n functions are linearly independent. Yeah. So that question. Yeah. So we raised before, and here we need to answer that question. Okay. Yeah. All right. So let's look at the linear independence of solution. So what do you mean linear? Yeah. Given several solutions, what's the meaning of linear independence? Yeah. Yeah. So we saw some definition before, yeah, but here for multiple functions. Yeah. I gave you the definition for two functions before. Yeah. C1, C2. Or y1, y2. Remember k1 times y1 plus k2 times y2. Okay. Yeah. And this function, so you can find constant k1, constant k2, linear combination of y1, y2 function, such that this function can never be that constant. Yeah. No matter, we should say in this way. For any k1, k2, yeah, for any k1, k2, this linear combination k1 times y1 plus k2 times can never be the zero function. Okay, the zero function. So that's the linear independence for two functions, y1, y2, two functions. Yeah. But here we need to extend this definition for n functions. Yeah. All right. Homogeneous second order linear ODE. Yeah. Yeah. But for homogeneous second order, then we only consider y1, y2, right? Yeah. Because the basis, to get a basis, we only need two functions, y1, y2. Yeah. All right. Assume that y1 of x and y2 of x are two of the solutions of the above ODE. Yeah. Yeah. Then, question: under what condition that y1 and y2 are linearly independent on any open interval I? So here you can see we frequently use that open interval I. Okay. Yeah. Yeah. So we need solution on some open interval I. Okay. Yeah. All right. Interpretation. Yeah. So what do you mean linearly independent? Right. So we need some interpretation. We call y1 and y2 linearly independent on I if the equation k1 times y1 function plus k2 constant times y2 function equals 0 on I implies on I. So here you can see this equality holds on the whole interval I. Okay, on I means everywhere in that I. Okay, the whole interval I. Yeah, implies that. Yeah. So if you have this condition, it implies that. Yeah. Oh, new student join us. Yeah. It implies that K1 must be 0, K2 must be 0. Okay? So that's the definition for linear independence. Yeah. So, or if you assume, yeah, so that means if you assume you have this equality, but this equality holds on this whole interval I, yeah, then you cannot find non-zero K1, K2. Okay? Yeah. Okay. So in other words, this equality forces K1, K2 must be 0. That's the meaning of linear independence. Okay? Yeah. Yeah. In other words, if we look at in the opposite way, if you can find non-zero K1, K2 such that this inequality holds, then we can say y1 and y2 are linearly dependent. Yeah. Linearly dependent, not independent. Okay? Yeah. Yeah. All right, so that's the meaning. Yeah. Then let's do some exploration. Yeah. So what can we get? Yeah. From this condition? What can we get? Yeah. All right. We take the derivative. Yeah. We take derivative on both sides. Yeah. Yeah. We can do it, right? Yeah. So if you take derivative, because K1, K2 constant. Yeah. So you just take the constant out. K1 times y1 prime plus K2 times y1 prime equals 0. Here you can see you get another equation. Yeah. So here let's call it equation. Okay. Another second equation. So you have two equations, right? Yeah. The given condition, that's the first equation. Then you derive a new equation. Yeah, this y1 derivative. Yeah. y1 prime, y2 prime. So you get a second equation. And in these two equations, you can write as a linear system, right? Yeah. Yeah. You can put them together, you get a linear system. Yeah. But this linear system is a special linear system. The right-hand side equals 0. So we call it homogeneous linear system. Okay? The homogeneous linear system. Yeah. So it's a 2 by 2. Yeah. So we can represent as a matrix form. Okay? Yeah. Yeah. Here, K1, K2 we treat as unknowns. K1, K2 we treat as two unknowns. All right? Yeah. Because y1, y2, they are solutions. Yeah. So y1, y2, we treat them as the known solutions, known functions. Yeah. Known functions. Known solutions. Yeah. y1, y2. Yeah. All right. So you have this homogeneous linear system. Okay? All right. All right. Then, here we need some knowledge from linear algebra. Yeah. So this part, based on my experience last year, most of you, do not feel very comfortable about linear algebra. Yeah. So here, let me ask you one question. In linear algebra, under the current situation, here our situation is we have a, 2 by 2 linear system. Yeah. The linear system, homogeneous linear system with the coefficient matrix 2 by 2 matrix. All right. So here you can see we want to determine the solution of this linear system. Yeah, because K1, K2 unknown. Yeah. In order to find K1, K2, we need to solve this linear system, right? Yeah, we need to solve this linear system for K1, K2 unknowns. Yeah. So here's the question. Yeah. First, this linear system, by observation, it must have a trivial solution, right? When K1 equals 0, K2 equals 0, then it satisfies this linear system. But that, because K1, they both 0, we call it trivial solution. Trivial solution. Okay? The linear system has a trivial solution all the time, right? No matter what y1, y2 are, this system always has that trivial solution. Yeah. All right. The first observation. Second, we want to ask, is it possible that this linear system has some non-trivial solution? Or you can ask in this way, under what condition this linear system has a non-trivial solution? So you need to use some knowledge from linear algebra. So there is a result telling you under what condition this linear system has a non-trivial solution. Yeah. All right.
So when they're linearly dependent?
Yeah. Right. Yeah. Linear independent. Yeah. So here, when we solve this linear system, the result is related to the linear dependence and the linear independence. Okay. Yeah. The solution of because when we get a trivial, non-trivial solution, we can make a conclusion if these two y1, y2 solutions are linearly dependent or independent. Okay? Yeah. So, but here we ask another question. Okay? Another question. So here you do not use linear dependent or independent. Okay? So here you use our linear algebra result. There is a result. You know this is determinant, right? Yeah. Determinant of this coefficient matrix, 2 by 2 coefficient matrix. When the determinant not equal to 0, what's the conclusion? If the determinant is not equal to 0, then there is no non-trivial solution. Okay? So the only solution is that trivial solution. If the determinant is non-zero. Yeah. If the determinant equals 0, then there is non-trivial solution. Okay? There is non-trivial solution. Under the condition the determinant equals 0. That's the result from linear algebra. Okay? Yeah. So then, based on this linear, now we go back to linearly independent. Okay? Yeah. After we apply this result in linear algebra, then we can go back to make conclusions related to linear dependence and the linear independence. Yeah. So the conclusion is like this. All right. Yeah. So you find two solutions of that homogeneous system. Okay, y1, y2. Yeah. Then you calculate this determinant. Okay. Yeah. So you only have two cases, right? Equal 0 or not equal to 0 on that interval I. Okay. On that, because you look at the value on this interval I. Okay. Yeah. Not equal to 0 on that I, then you only have trivial solution. That means your y1, y2 solution linearly independent. Okay, yeah. By definition, right? Yeah. So your y1, y2 solution must be linearly independent. Yeah. If this determinant not equal to 0. Yeah. Then the other way, if the determinant equals 0 on I, okay? So if when you say determinant equals 0 on this whole I, okay? On that whole I, then your conclusion is, yeah. Actually, yeah. So I will explain. Actually, equals 0 on at one point in I. Okay. Yeah. I will discuss this later. Yeah. All right. So if the determinant equals 0 at one point in I, so you do not require everywhere in I, just one point in I, okay? Yeah. Because at that point, so here let's assume that point is x1, okay? We just use the special x1 point in that I. At that x1 point, this determinant equals 0. Then what's the conclusion? At that point, equals 0. Yeah. K1, K2 has a non-trivial solution, right? So you can find a non-zero K1, K2 such that it equals 0. But only at you find that only at x1, right? Yeah. Only at the x1 it's 0. At other points it may not be 0, right? Yeah. Because in that interval I you have many other points. Yeah. All right. Yeah. So here we need to be very so actually this part is very easy to get confusion. Yeah. Very easy to get confusion. Yeah. All right. Yeah. So actually, so you can see when you look at the non-zero case, okay, non-zero case, you only need this true at one point, okay, at one point in I, okay, yeah. But for the equal case, then you need equal to 0 on the whole I. Yeah. If it's not a whole I, then you can find a point. It's not equal to 0, right? Yeah. Yeah. So this place very confusing. Yeah. This place very confusing. Yeah. All right. Yeah, because here we call this linear input on I if equation equals 0 implies connectivity 0. Okay, yeah, equals 0. Because equals 0 on I, that means everywhere, right? Yeah, everywhere on that I, not just one point, everywhere on I. Okay, yeah. But if at one point, one particular point, x1, that is not 0, then the condition is not satisfied, right? Yeah. So here the condition is equals 0 everywhere on I, implies K1 equal K. That's the meaning of linearly independent. Yeah. Yeah. So here, the main confusion point is. Yeah, so here, let me put the main confusion point. Okay, main confusion point. Now, you need to consider these two cases. Okay, two cases. The determinant. So that determinant. Okay. So that determinant. So I just represent that whole determinant. Not equal to 0 on one point in I. Okay? Alright. So then another case is the determinant equals 0 on the whole I. Okay? These two cases. So that's the linearly dependent case. So the first case is the linearly independent. Okay? Linearly independent. Second is the linearly dependent case. Linearly dependent, you need to make sure on the whole R. Not just one point. One point is not good enough. Okay? Must be everywhere in that interval R. But for linear independence, one point not equal to 1. It's strong enough. It's good enough. Okay? So that's the main confusion point. Okay? When you apply this result. Because later I may assign you. I remember. I may assign you a sequence of, similar questions, about linear dependence, independence, and the determinant equals 0 at one point, or determinant equals 0 on the whole interval, So, that kind of statements, similar statements. So so probably, let me see. Before I assign you those questions, I like to give you two such examples first. So in class, I can give you two such examples and compare their difference. In that way, so hopefully you can understand better. Otherwise, it's not easy to understand this result well. All right, so that's this topic, linear independence. And later this result can be generalized to n, nth order linear ODE, homogeneous. All right, So, but that nth order, higher order ODE, so we leave to module 3. Okay, module 3 we will go to higher order ODE. At that time, we will have the similar result, generalized result of this one. Okay, so we finish part B. So next we will move to part C. I will talk about Laplace transform. But we are near the break time. How about let's take a 10 minutes break first. So after the break time, we study the new topic, Laplace transform new topic after the break time.